So let's talk about work and kinetic energy. And if you want to write stuff down, you can. As always, it'll be posted shortly. Please remember, I will post the lesson that you guys are to watch. I'm going to post that after I do this so that it's in the right order. So I told Mr. McDougall I think it's Friday or Monday, I can't remember. Maybe it's Monday. Monday, you guys should watch that, the lesson on springs. Okay? And just log into Schoology, find it, and play it for her, okay? Right, here we go. So, we've already mentioned this before. When work is done on an object, it may give it kinetic energy. As you push something, it increases in speed, right? You are increasing its kinetic energy. So in general, work done, FD, as always, I keep coming back to this, when work is done, energy is transferred. And when something begins to move, then kinetic energy is gained. And that work done is equal to the kinetic energy. Or you could say delta EK, change in kinetic energy. The work done is the change in kinetic, in kinetic energy. Some books like to label it as delta KE. I'm losing my voice. KE, kinetic energy. Right? So delta EK, delta KE, all the same thing. All good? So, what is this magical formula for kinetic energy, for EK? Oh. We don't need that. I think I was playing around with PowerPoint back in 2002. Sound effects. That was cool back then. Is it? Good point. Since W is FD, and remember our old friend F equals MA, we can put this MA in for F. And what do you get? Come on.
Mad.
You get mad. W equals mad. Now, do you remember this old friend? VF squared equals VI squared plus 2AD. Think we can work some magic here with this and that? The answer is yes. If the object is at rest, VI is, the object is almost always at rest, then the VI would be 0. And then you get AD, if you solve this for AD, the VI disappears, right? And you get AD would be VF squared, or just V squared over 2. And so, now this is going to go in there, and what do you get? W equals M V squared over 2. Substitute this in for the AD, and you get work done is the kinetic energy gained is equal to FD, which is equal to mad, and blah, blah, blah. Through the magic of algebra, kinetic energy is mv squared over 2. One of the simpler form of derivations. EK equals mv squared over 2. Sometimes you see it like this. EK is 1/2 mv squared. They mean the same thing, right? Times by a half, divide by 2, same thing. Right? Now, if there is a change in VI, if that is different, then there's going to, like, in other words, if the VI is not 0, then change in kinetic energy, what can you change over here? Only the V, right? So if it's a change in kinetic energy, then it's m delta V squared over 2. You'll see that in the sample questions. I don't know, is that even worth? I was clearly enamored with animations in PowerPoint. That's like exactly the same slide, isn't it? Moving on. If an object is already moving, the work done is the change in kinetic energy, and the work done is delta Ek, or EKF, final Ek, minus EKI, initial Ek. And again, that is going to come out in the sample questions, which I think you do have, right? Yeah. Excellent. Do you like having the whole unit sort of all ahead of time? Yeah? Maybe I'll do more of that with trade calls.
Yeah, we all definitely do that.
And the Oscar goes to kinetic energy samples. Excellent. Let's look at these here. I thought I had this all cleaned up a bit, but I guess I didn't. Okay, so there's only 4, it looks like. So a force of 25 newtons acts for a distance of 60 meters upon a 2 kilogram object, which was initially at rest. Assuming no friction, find its final velocity. So the F is 25, the D is 16, the mass is 2, the VI is 0. Find its final velocity. Okay, so a lot of these questions you're going to see are kind of, oh yeah, Blaine, you weren't here, were you? Okay, so you guys, okay, so what I was saying was you will find a lot of these questions are sort of like kinematics and like dynamic questions, but you sort of approach them from a kinetic energy standpoint. Okay? So you see we have an F and a D, right? So I can find what? I can find the work, F times D, 25 times 16, which is 400 joules. So I've done 400 joules of work. Where does all of that work go? It goes into creating kinetic energy, right? So all of that goes into Ek, which is mv squared over 2. So 400 is equal to the mass, 2 v squared. Conveniently, I've made it 2 so that the 2's do what? Cancel. You, of course, won't have that luxury on a test. So that means that v is the square root of 400, which is conveniently 20 meters per second. Right? The work is done, converted to kinetic energy, and then you take that kinetic energy and you find the speed. Number 2. A force of 8 newtons acts for a distance of 5 meters upon a 4 kilogram body, which was initially already traveling at 4 meters per second. Find the EKI, find the work done, find the final EK, find the final velocity. EKI, initial kinetic energy. Okay. Watch the video later, Shaden. mv squared over 2. So the initial kinetic energy, the mass is 4. The velocity is also 4 squared. So 4 squared is 16. 4 16 is 3264. Divided by 2 is 32 joules. It has 32 joules of kinetic energy. J's look a lot like 5, don't they? Work done. W equals FD. 8 newtons, 5 meters, 40 joules of work. The object had 32 joules of kinetic energy to begin with. And then 40 joules of work was done. So now, what would be the final EK? Subtract. You'd add them, right? You're adding work. You're adding more kinetic energy, right? So yes. In fact, you could say, if you want to be mathematical about it, and who doesn't, work is EKF minus EKI. Maybe that's why you thought subtract, Tanner.
Well, I got the, if you want to find the change.
Yeah. Well, the change is plus 40. So the change, the work done is 40. You solve for EK. Oh my goodness. You solve for EKF. That's no better. And then that's going to be minus the 32. But when it goes to the other side, EKF is going to be 40 plus 32. 72 joules. Right? You're adding work. You're adding more. And so what is that final velocity? Once you've got that EKF, mv squared over 2, 72, mass is 4, v squared over 2. 4 divided by 2 is 2, 72 divided by 2 is 36, v equals 6, right? Yeah, good. Obviously, we're getting a little bit more challenging. Okay, so this time we've got a 2 kilogram mass. Initially moving at 20 meters per second, it slides 150 meters on a rough surface where it experiences a force of friction of minus 2. Find the EKI, the work done, the EKF, and the final velocity. This looks exactly the same. What's the only difference? There's friction, so instead of adding to kinetic energy, you're actually subtracting. In fact, the work done is going to be a negative value, isn't it? Right? So it's going to be exactly the same. EKI is going to be mv squared over 2. 2 kilogram mass, moving at 20 over 2. 2 divided by 2 cancels out. 20 squared is, we have 400 joules of kinetic energy to begin with. The force is negative. So that's going to be FD. So really, should we put that negative in there? Yeah. So minus 2 times 150 minus 300 joules of work. We're taking it away. Mathematically, algebraically, you should probably do this. EKF minus EKI. So that's minus 300. We're solving for EKF. And that's going to be minus 400. And when it goes to the other side, it becomes positive, right? So it's 400 minus 300 is EKF, or EKF is 100 joules. The object lost 300 joules of energy. Where did it go? Heat. Energy must be conserved at all times. Quite often, the thief is heat. Find the final velocity, EKF, mv squared over 2. 100 mass 2 v squared over 2. What's the velocity going to be? 2's cancel. V squared is 100. V is going to be 10 meters per second. Normally I would say go ahead and try number 4 on your own. Do you want to try it? I saw a no and I saw a yes, sure. But you know what, I'm just going to do it because Bailey's got to go. I got things to do. Let's just get her done. This time we're looking for the distance. Through what distance must the 5 Newton force have acted in order to change the velocity of a 4 kilogram mass from 10 to 15? It slowed down. It was already moving at 15. Here it's moving at 10. No, sorry, I got it backwards, don't I? From 10 to 15. I thought it was a friction thing. From 10 to 15. Always pays to read the question twice, right? Yes, because this is a push, it looks like. So it's increasing from 10 to 15. So how am I going to find the distance? Is this not sort of this type of question, just kind of moving backwards in reverse? Right? How am I going to do this? What's the logic here? Can you find the EKI? Yeah? You know the mass, you know the speed? Can you find the EKF? Yeah? If you subtract them, what does that give you? It gives you the work. And from the work, can you find the distance? And the answer to all of those is yes. So EKI is mb squared over 2. You can probably do it on the paper there without even looking up. Mass is 4. Initial velocity is 10 squared. 10 squared is 100. 200 joules of kinetic energy to begin with. 200. Mass 4. New velocity 15. Ooh, I can't do 15 squared in my head, I don't think. Or can I? 225. Times 2. 450 joules. The kinetic energy went from 200 joules to 450 joules. How come? Somebody did some work. The work done is the change in kinetic energy. So that's going to be 450 minus 200. Somebody did 250 joules of work. And now W equals FD. That's 250. 50 meters, I think, right?